So hello everyone, and so in the last lecture we studied how to calculate the metal-metal bonds in a mineral complex, for which there are certain rules that needs to be followed. Okay, so let us again start from there because we need to solve the questions like calculate metal-metal bonds. So how do we do this? For example, if your complex has n number of metals, and there is some vegan system as well that I'm not talking about. We're not concerned over here about the vegan system. We're just talking about random any complex that has more than one metal in it. Then only the question of metal-metal bond comes into existence, right? So, for example, there are n number of metals in a complex. Then how do we calculate the metal-metal bond? So for that, first of all, you need to calculate, for each metal in a complex, you need 18 electrons to be fulfilled for the stability, right? So for n metals, it could be how much electrons you need? N into 18, right? So this is the total number of electrons you need to make that complex stable. But since that complex is not a complex of one metal, there are more than one metal, and so there's a chance of existence of metal-metal bond also in the complex. So in that case, in those cases, you don't have to count 18 electron per metal, right? So in that case, what you do, you calculate that how much total electron you might have needed if those were different complex, those metals. But you need to subtract it by total electron count of that metal complex, the total electron count that exists in this metal complex. So this is the number of electron that metal complex should have if there was n different complexes, okay, having no metal-metal bond. But there's a chance of metal-metal bond. So this 18 electron per metal is not valid here. So you need to subtract it by the total valence electron count of the metal complex. And we already studied in the table 2.2 how to calculate total electron count. And I hope that it is clear. And then you need to divide. Now that this will give you number of electrons that should have been there, but is not there in order to complete the in order to for the stability, right? So you need to subtract. So you get that number of electron that is needed for the formation of 18 electron per metal, and then you need to divide it by 2. So that will give you the number of bonds, right? Because anyways, if the complex has n number of metals, you really need 18 into n number of electrons. Okay. Now, so that will give you this formula. Now let us use this formula and solve questions. The question is given in table 2.3. So these are molecules that you need to calculate the metal-metal bonds. Let us start and calculate the metal-metal bonds, number of metal-metal bonds for each molecule that is given in table 2.3. So first is Fe3CO12. So the first thing that should come into your mind, that how much total number of electrons it should have. It should have 18 into 3. Okay, and how much metal-metal bond? Sorry, how much electron in this complex really has? That is the total valence electron counted. So for iron, so I am considering neutral atom method all the time. So for iron, it is 8. So 8 into 3 you will do the calculation. 8 into, we are calculating the valence electron. 8 into 3 for metal iron, 3. And then 12 into 2, you need to add again. 12 into 2. Now this will give you the valence electron count. Okay, so this is equals to 54, and this is equals to 48. So which gives you 6. Now, in order to calculate the metal-metal bond, you need to divide it by 2. That means 3. Okay, there is 3 metal-metal bonds, and then there's another column which tells you to calculate metal bonds per metal. Okay, so when in such cases, this is a metal-metal bonds present in the complex, but you need also, for example, you got to know that there are 3 metal-metal bonds, but now iron is, there are 3 irons in the structure, so 3 irons. If you have just knowledge of total number of metal-metal bonds, then probably you cannot make the complex or the metal structure of the complex, because this you don't know how much bond each metal carries. So these 3 bonds you can make here also, and you can consider another iron is doesn't have any metal bond with other 2 iron. Okay, so there's a confusion right now. So in order to get rid of this confusion, you need to calculate one more parameter, that is metal bonds per metal. Like per metal, how many bonds are there? So in that case, you need to, since you have already calculated total valence electron, so you need to consider total valence electron, and then you need to divide it by total number of metals. Okay, here 3. So that will give you the value of 16. Okay, so for that has given us the value of 16. So in this case, you are 16. So what does that mean? So this indicates that in the complex, each metal is kind of 16 electron, right? So in order to fulfill 18 electron, this metal needs 2 more bonds. Okay, so it will form 2 more bonds. That is 2. So there is 2 metal, or we can say there is 2 bonds per metal. Okay, so now let us draw. So we already got into the answer that there are total 3 metal bonds, and there is 2 bonds per metal. Now let us draw it. So there is 3 metals, and there is 2 metals, 2 metal bonds between per metal. Okay, so one metal is forming 2 bonds. So if there is only one way of drawing it, it's like this. So each metal you see is forming 2 bonds. Each metal is forming 2 bonds, and there is total number of metal bond is 3. So this is the only way you can draw the framework here. Okay. Now similar question is this one. Let us solve it. Okay. So cobalt 4, Cu whole 12. Okay. Okay. So let us proceed. So in case of this complex, you need total of 18 into 4, that gives you 18 into 4, that gives you 72. Okay, 72 total electrons. And what is the valence electron count of this complex? So 4 into 9, that is 36, plus 12 into 2, 24, that gives you 60. So if you subtract it and you divide it by 2, then you will get the value of 6. So there is total 6 number of metal bonds. And also you need to calculate the metal bonds per metal. So in that case, you need to consider the total valence electron, which is 60, and you need to divide it by total number of metals present in the complex, that is 4. So you get total 15. So it is coming as 15 electrons per metal. Okay, so you need, so how will you say this? It is coming, there is total number of 16 electron for 4 metals. That is why there is, when you are like uniformity, considering uniformity, then in case you got 15 electrons per metal, but it should be 18. So there's a gap of 3. So that is why there is 3 metal bonds per metal. So how did draw it? So there's only one way of drawing it is this. Okay, so there is total number of metal bonds is 6. So 1, 2, 3, 4, 5, and 6. And per metal bond, how many per metal, how many bonds? 3. So this is the only way. Okay, so let us move forward and take difficult problems. Now this is molybdenum complex, and this is a dimeric complex. So everything you will calculate, you will multiply by 2 because there is 2, right? And in the outside. So for in case of molybdenum, how many electrons? 6. It needs, okay. But before that, you need to calculate. There is two molybdenums are there. So 18 into 2, that is 36. Okay, and you need to count the valence electron. So how many valence electron? So we are calculating it for this one, and then we multiply 4 by 2. So molybdenum is 6. Okay. From neutral atom method, Cp eta 5 will give, it is L2X type. So from the neutral atom method, it would give how many? 5 electrons, sorry, 2 plus 2 plus 1, that is 5 electrons. And carbonyl is L type, so it is giving 2, and there is 2, so 4. And you need to multiply everything by 2 because there is 1 2 outside. Everything is repeated twice. So that will give you 15 into 2, that is 30. So you got 36, and if you subtract 30 from it, the valence electron count, and then divide it by 2, and that will give you total number of metal bonds, that is coming to be 3. And how many bonds per metal? It is 30 divided by 2, that is 15. Again, 3 more electron you need to complete the 18 for each 18 electron for each metal. That is why there is 3 bonds per metal. So only way to draw 3 bonds per metal is there, and you have total number of 3 bonds between 2. There is only 2 metal in the complex. So it's very easy. The job is easy. In this case, you need to draw these 3 bonds. This is the only way of drawing it, right? So I think this rest to let us solve these also. Okay, so this one, eta 4 C4 H4. Okay, so how many? First of all, 18 into 2, that is 36. Okay, now let us calculate the valence electron count for this complex. So for iron, it should be 8 into 2 plus, there is a ligand, it is written eta 4 C4 H4. So eta 4 is already given, and C4 H4 is basically how much? It's a neutral atom, right? It is CnHn, right? So it is neutral. So eta 4, that is, which is L2 type. So it is giving total how many? 4 electrons, and there are 2 such things. So 4 plus 4, that is 8. And then you have 3 carbonyl, that will give 6. Okay, so how much it came out to be? So if you calculate, then it comes out to be 30. Okay, so that is why you will now do 36 minus 30, and you will divide it by 2. So that will give you 3. So there is 3 total number of metal bonds, and metal bonds per metal, it would be 30 divided by 2, that is 15. Again 3. So again the value is same. So let us take the simplest example of all the time. It is iron to carbonyl line. Okay, so okay, it should be 36 electron, 18 into 2. Okay, and how much it really has? That is how we calculate the total valence electron. So 8 into 2, 16. plus 9 into 2, 18. So 16 plus 18 gives you 34. So that if you subtract and then divide by 2, you will get the value of 1. So there is total number of, how many total number of metal bonds is there? 2. Sorry, 1. Okay. So in such case, do you really need to to calculate the bonds per metal? No, right? It will be 1 only because this only came out to be 1, but let us calculate it in chemical form. So you got the total valence electron to be 34. So you need to divide it by 2, which will give you 17. You need 18. Okay, so that is only one. There's a difference of 1. So there is one. So this suggests that there is total number of one metal bonds, and each metal carries one metal bond. Okay, I hope I'm clear, and now there is no problem in calculating the metal bonds in the multi-nuclear complexes, and also calculating bonds per metal. So, in drawing the most probable structure of a given compound, the metal core is written first. So you write the metal core first. So you need to draw the bonds also. So that is why this formula comes into picture. So the carbonyl group and the other ligands are arranged on the metal in such a way that each metal follows the 18 electron, right? So we consider that in mind, and that is why this formula also considers that in mind, that there should be 18 electron per metal. Okay, and the carbonyl group can occupy either a terminal or a bridge position. We know that carbonyl can act both ways. Okay, it will give 2 electron only, but it can be in the form of bridged ligand and also can be in the form of terminal ligands. The terminal ligand means only connected to single metal. Bridge means connected to more than one. Okay, so to illustrate this complex, let us consider this complex. Okay, actually we have already done all of these, but then also let us calculate again. So this is a radium complex. Okay, now there is mu CO whole twice. So this is this carbonyl is bridging, but you don't have to get confused over there. Carbonyl can only donate 2 electrons, right? So you will consider 2 only here. So in this case also 2. So 2 carbonyls is there, 2 into 2. Okay, then eta 5 Cp. So I am calculating by the neutral atom method. In here, it is calculated by the the oxidation state method. So eta 5 will have 5 electron. And radium is 9. And you need to multiply it by 3 because there is 3. And then again, there is normal 1 carbonyl. No mu is written. That means it is terminal carbonyl. Sorry, carbonyl. Now, if you calculate it, then it is 48. Okay. Now, but it should be how much? It should be 18 into 3. Okay. That will give you how much? 54. So you need to subtract 54 and 48 and divide the resultant number by 2. So that will give you 3. So there is total number of metal bonds. Metal bonds is 3. Now, in order to draw the core of the metal complex, you need to know the number of bonds per metal also. So in order to do that, you need to divide the total valence electron by total number of metals. So here 3. So that will give you 16. So in order to make this 16, 18, there's a difference of 2. So that means there is number of bonds per metal atom is 2. Okay. So there is 3 metal. So let us draw the complete structure and not just the core structure of this complex. So there is total 3 metal bonds. So draw radium in such a way that there has to be 3 metal bonds and 2 bonds per metal. So you draw triangular core. Now let us put all the metals, all the ligands as well. So start. There is 2 bridged carbonyl. Now bridged carbonyl can be in these 2 radium. All the 2 bridged carbonyl can be here, or one british carbonyl is here, one is here. Okay, but in that case you need to calculate. So let us first go with simple. There is cp. So this cp ligand is all the in all the three radium. Okay, there is 3 cp. So let us draw 3 cp. Now there is one terminal carbonyl. So draw one terminal carbonyl to any one radium, and let us leave this new 2 carbonyl for later. Like in after 1 minute, we will draw that. So calculate the electron count for this radium complex, because this radium complex has more players in comparison to other radium complex. So I'm considering the neutral atom method again. So here we have 9 plus 5, that is 14, plus 2, that is 16, plus 1 plus 1, that is 18. So this radium already has 18 electrons. So this means that this 2 carbonyl will be there in this 2 radium and not in this radium. So draw 2 bridge ligands. Now calculate the electron count again. 9 plus 5 gives you 14. Count the metal. 16, 17, count the electron. 18, 19. Okay, so you can consider 1 electron also, or you can consider 2 and 0. 2 and 0. So this way you can consider. I hope it is clear now. We can draw it, right? Now let us start a new topic, which is compliance and violation of the 18 electron. So sometimes there is violation of the 18 electron rule, right? So not all the time the metal complex has 18 electron rule and is common in nature. There are complexes that exist in nature that is not 18 electron rule also. Then also it exists. So what are, where like, when is such cases considered? So let us study those. While a large number of organometallic complexes, especially those possessing strong ligand fields, such as carbonyls, obeys 18 electron rule, but there are many complex, like those of early transition metals, like titanium, zirconium, vanadium, and also the square planar late transition metals, such as rhodium, palladium, platinum, which do not obey the rule. To find an explanation, the basics of the molecular orbital interactions in a typical organometallic complex have to be understood first. Okay, so mostly we know that 18 electrons should be followed in order to maintain the stability of the metal complex. But the initial transition metal complexes, that is the titanium, zirconium, vanadium, this already has very low electrons in the metal orbitals, right? So in such complexes, it is seen that the 18 electron rule is not followed. And also, when the complex is not octahedral, rather if it is square planar and all of those, in that case, square planar or tetrahedral, in those cases also 18 electron is not followed. So what is the basis of this, and how do we know that when it is following and when it is not following? So in order to study this, we must know the depth, that is the molecular or orbital diagrams. So we need to know some basic principles about the molecular orbital diagram and what really happens, and where this 18 term comes from, and why in some terms, why, and also why certain, there are different types of ligands also. There is sigma donors, pi donors, pi acceptors. So why some ligands are sigma donors, why some ligands are pi donors, and why some ligands are pi acceptors, and what is the molecular orbital diagram in all of these cases? So that we will be studying. So that we will only get to know when we will see the molecular orbital diagram and see the molecular interaction involved. Okay, so this is a pictorial representation of MO diagrams of a sigma donor and a pi acceptor ligand. So when there is sigma donor, there is electron donation from ligand to metal, pure electron donation from ligand to metal. There is no back. Okay, so this means that the ligand electron is given by the ligand to the lower orbital of the shared orbital. That is this is the atomic orbital of the ligand. This is the atomic orbital of the metal. This is the shared molecular orbital. So this means that in order to form bonds, you need to give the electron from the atomic orbital to the molecular orbital of the metal ligand. Okay, and only when the ligand is giving 2 electrons and fulfilling this orbital, then it is sigma. So this is how it shows. And if it is pi acceptor, so in that case, metal is going to give the electron in the bonding form to the anti-bonding orbital of the ligand. Okay, so these are the two molecular orbital diagrams, which is important also. Now, information on the compliance of the 18 electron rule can be obtained by considering the molecular orbital picture of the complexes. The sigma only MO diagram of an octahedral complex, figure 2.2, indicates that there are 6 bonding orbitals which are closer in energy to the original ligand group orbitals. So these can accommodate a total of 12 bonding electrons from the ligand. Okay, now most of the organometallic octahedral complexes which obeys the 18 electron rule have pi acceptor ligands. So in those cases, the electrons from the metal can be accommodated in the T2G orbital, which is purely sigma. Only consideration are non-bonding, but becomes bonding when pi back bonding is considered. For example, in the case of MoCO6. So let us consider, okay, all of these. The strong sigma donating ability of the carbon monoxide raises the energy of the Eg star orbital, okay, making them more anti-bonding, while its strong pi acceptor ability helps to stabilize the T2G orbital further as bonding orbitals. Now these T2G orbitals can now accommodate another 6 electrons, and thereby making total 18 electrons. 18 electrons. So this is the molecular orbital diagram of a sigma only ligands. So these ligands are sigma donors. Okay, but you know, only when if it is pi donor, pi acceptors, it can fulfill the 18 electron rule. Okay, and mostly to see that the complexes that has pi acceptor ligands fulfill the 18 electron rule wonderfully. So this is the molecular orbital diagram for the sigma only ligands. So in those cases, you have 6 orbitals, 6 bonding orbitals that can accommodate 6 into 12 electrons in total. Okay, that is very close to the ligand. Okay, but there is T2G, which is non-bonding. Okay, because it is pi symmetry, so it is non-bonding. No symmetry matches with the ligand orbitals, and there is the anti-bonding for all these bonding orbitals. Okay, so this 6 ligands octahedral complexes we are talking about. So this 6 ligands can give 2 electrons each, fulfilling this 16. Okay, sorry, say this 12, 6 into 12 electrons here. But in order to have 18 electron complex, now it needs now how many? 18 minus 12, that is 6. So where the 6 electron comes from? So this can only come from metal when it is going to back donate its electron. So this metal now then back donates to the non-bonding T2G orbitals. And since it is back donating, so now there will be electron in the T2G orbital, which is non-bonding, so making it a bonding character. And that is why it is total 18 electron or 18 electron complex. Okay. A similar situation can be seen in the MO diagram of sandwich compounds such as ferrocene. The electrons are filled in the bonding and also the non-bonding orbital. Because wherever there is pi bonding, pi back donation taking place or pi donation taking place, then there has to be some non-bonding orbitals that needs to be filled in order to complete the 18 electron rule. And the HOMO is the non-bonding. Okay, so the energy level diagram of bis benzene chromium, another 18 electron sandwich complex, is quite similar to that of ferrocene. For complexes having pi or sigma donor ligands, the possibility of violation of the 18 electron rule is therefore more frequent. But for pi acceptor, it is not, right? We already saw. So this is the crystal field splitting diagram of various geometries showing approximate energy levels. Okay. So this is, we know for the octahedral is T2G and EG, and it is very much stable. Okay, so that is why we call that octahedral complexes are very stable, because this crystal field splitting energy is very much. For tetrahedral, it is very small. That is why they are not that much stable. And it arranges in T, E and T2. For square planar, it is like this. Stable, more stable than the tetrahedral, but less stable than the octahedral. And there is trigonal bipyramidal. So these are the various splitting things. Okay, that needs to be learned. For a 5-coordinate trigonal bipyramidal complex such as iron CO whole 5, which obeys the 18 electron rule, the crystal field splitting diagram figure 2.3 indicates that 4 of the metal-based orbitals have negative crystal field splitting and are low in energy, and only one orbital is antibonding. You can see here 4 is positive, has positive crystal field splitting energy, and only one is antibonding. Okay, so these 4 bonding and non-bonding metals based orbitals can accommodate total of 8 electrons, and the 10 electrons donated by each 5 ligand, so making it 18 electron. Okay, so this is how this 5 coordinated complex, not octahedral, but then also obeys 18 electron. Okay, for tetrahedral complexes, 18 electron rule doesn't appear to work. Okay, for tetrahedral and for square planar, this doesn't work. So for tetrahedral, how many electrons you can fulfill? So tetrahedral is 2, so total 4, and 4 by the ligand also. So 4 into 2, 8. So 8 plus 4 is 14. Okay. And how do you get more electrons? Let us study what is there. So for tetrahedral complexes such as nickel, carbonyl, gold 4, which obeys the 18 electron rule. So some of the tetrahedral complex does obey 18 electron rule. So how does it do that? The practice adopted so far is explaining that compliance with the 18 electron rule does not appear to work, since 4 ligands will supply. So this is 4. So 4 into 2, 8 electrons, and only 2 orbitals have negative crystal field. However, in tetrahedral complexes, the magnitude of splitting sense is very, very small. That is why the both the T2 and the E sets of the orbitals can donate electron to the pi etc. orbitals of the carbonyl ligands, leading to a bond interaction. Okay, since splitting is very, very small, and that is why it shows the band donation of the metal to ligand by all these, both E and T2. That is total of 5. That is 10, right? So 10 plus 8, that is gives you 18. A clear violation of the 18 electron rule is the case of the square planar organometallic complexes of the late transition metals. So the square planar complexes doesn't show 18 electron rule. So as shown in the crystal field splitting parameters, 4 of the d orbitals either have a negative or a small positive crystal field splitting, figure 2.3. Now, one of the orbital, the d x square minus y square, has a very large positive crystal field, so that you won't consider to be donating to the ligand. Okay, so there are four electrons, so 8. Now, how many d orbitals are participating in the back donations of the metal? So it is 4. So 4 into 2, again 8. So 8 plus 8, it makes only 16. Okay. So in addition, many organometallic complex of the early transition metals also violate 18 electron rule because they have only less number of electrons to back donate. So the possible energies reason of such of the orbitals of these complexes are too high in energy for effective utilization of the bonding or the ligand are mostly sigma donors. Okay, and many high valent D0 complexes have a lower electron count than 18. Also, sterically demanding bulky ligands force complexes to have less than 18 electron, right? So this is understood. Now the 18 electron rule fails when the bonding is in moderate to big or organometallic clusters are considered. Now the bonding of clusters and their stabilities are therefore considered under other electron counting rules also. Also, the rule is not applicable to the organometallic compounds of main group and those of lanthanoids and actinoids. All of these rules are only restricted to the metals having d orbitals, that is the transition metals. So the problems and the exercise will be solved in the next lecture. I hope that I am clear. Thank you.